fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
With the Tacoma Sounds, they had a miscalculation as they were building it. And what they forgot to do is read the fine print in their calculations. Well, let's go back. We've been talking about integration, and we've been discussing different techniques and how we can go about integrating. And we've been doing this on a number of occasions, and also we've been looking at, every so often, this whole entire fundamental thermocalculus. And do you remember how the fundamental thermocalculus was started, how we went about calculating it? We had some kind of curve out in space, and we're trying to find the area under the curve. And the idea is pack it full of geometric shapes, congruent shapes, whose area we can easily calculate. Guys, you can pack it full with anything you want. You can pack it full of circles. And then you can put some triangles inside of here, and a rectangle, and some other circles. But that's going to be very complex to calculate doing it like this. So you say, okay, what can I do to make this more systematic? What can I do to make this easier? And we said, why not use a whole bunch of rectangles? Because then we can be more systematic about it. We can take the region, maybe from A to B, chop it up into equal pieces, and as we chop it up into equal pieces, we take the length of the interval, and that's what B minus A is going to represent. You can divide it by N, get your delta X. And then from there, you figure out what's happening with your next one, your next point, your next point, so on and so forth. And you would say, let's use maybe the left-hand point as I'm constructing these rectangles, figure out the height, and that's where we got the whole entire f of x sub k. And maybe it's the left hand, maybe it's the right hand, or maybe it's the midpoint. It really didn't matter so much. We just said, pick one of those values. We're going to multiply it by delta x because delta x is going to be the width. And this right here is going to correspond to the height. You would put it all together. You would sum them up. But then you would have an approximation, and you say, well, what can I do to make my approximation better? Well, you keep refining it like refiner's fire. There is no end in sight. And as you keep doing it indefinitely, you start converging to this whole entire idea of integration. And integration, again, is really the addition, the summation, small parts. And this leads to the whole entire idea of the fundamental theorem of calculus. And instead of using the summation, the sigma notation, what we did is we said we'll find the antiderivative, and then we'll do the evaluation from A to B, and we'll take this and plug this in. And it's really fascinating why this works, something you learned back in Calculus 1. But when you go back and you start reading the fine print as to why this is working, there's a few things that a lot of times we just kind of sweep under the rug. The first thing is this. In order for this to work out, where the small parts form the larger picture, is the function f of x is continuous on the region from A to B. If you don't have continuity, sorry guys, you don't have this. The next thing is, and it's a subtle thing as well, you're on a region that is finite. So as long as you have those two characteristics, you're going to be able to use the fundamental theorem of calculus. So you would have these proper characteristics. But what if? What if you decided to break one of these rules? What would happen? Would your bridge stay intact, or would it come crumbling down? I'm going to get something called an improper integral. And that's what we're going to look at here today. And there's going to be two different types. You're going to have a type 1, and this is where you break the condition of, let's take this from the finite realm and extend it out into the infinite realm. What if I'm integrating over some region, such as from 1 to positive infinity? Well, at first glance, if you look at this from a graphical perspective, if you have some kind of curve, and if you want to find the area under the curve, starts off at 1, and go to the value of b. If you keep adding more and more and more to it, maybe you have it over here now, and then maybe you have it over here as b races off towards positive infinity. You might at first think that this might diverge because you keep adding more and more to it. But it could converge because maybe the stuff that you're adding to it is not big enough, has enough magnitude to really tip this over into the realm of divergence. Maybe it's just really, really small. And the way that we could denote these is I can say, going from A to positive infinity, f of x dx. The definition for these types of integrals, it is a limit definition. You take the limit as b goes off towards positive infinity of the integral from a to b. It's not the fundamental theorem of calculus. I cannot use the fundamental theorem of calculus here. Why not? Because the fundamental theorem of calculus states the function f needs to be continuous, first off, and also the endpoints, they're finite. We're not pushing us into the infinite realm. I can also go in the other direction, maybe towards negative infinity. In here, we're going to have another limit definition. We're going to have a races off towards negative infinity. And not only can I go from the left side and the right side growing without bounds, I can have the left side and the right side growing out bounds at the exact same time. So instead of having just simply a one-sided it requires a little bit more care as we go about the calculations. So we'll circle back around here in a moment. Let's look at a few of these first off. Let's say if I have the integration from 2 to the positive infinity dx the graph looks bit infinity. So we're talking about this region down below. And the way that I'm going to work through this of a limit. And then I'm simply going to stop the clock. I'm going to ignore the limit for the moment. And I'm going to assess what's happening now with this integral. And if you note, it goes from 2 to b. And if you stop the clock from b going off towards infinity, right there. There are no issues of discontinuity on this region. So when I integrate 1 over x, of course we're going to get the natural log absolute value of x. Do the evaluation from 2 to b. And the only thing that's changing now is b. And then start the clock again. Now you have a Cal 1 problem. So it's really one extra layer, which you did back in Calculus 1. So the whole entire skill set of doing evaluations of limits is now coming in full force. And I can look at this from a graphical perspective. The natural log of b graph looks like this. And as b goes off towards positive infinity, so does the natural log, just kind of slow, but it's going to get there. So in this case, we don't have convergence, but rather we have divergence. So let me take the problem. Let's change it up a little bit. Suppose if there was a 2 right there. Well, if there's a 2 there, and you go about the integration, add 1 to it, coefficient down below, evaluate, 2 to b, take everything, start plugging it in, and maybe just recondition it because there's a lot of negatives up here. Must be more positive. And now take this, drop it in. And now we see b's changing. 1/2's not. But this piece right here, that's getting closer and closer to 0. So we do have convergence. And this makes you think, well, how could this be? I'm adding up a bunch of small parts. I would think it's going to diverge as I keep doing it over and over and over again. But the small parts that I'm adding up are very, very small. Now, the scientists would look at this and really start questioning. Because when you look at both of these problems, where I have from 2 to positive infinity, and I had dx over x, we found that this actually diverged, whereas this converges. And a scientist will say, what's going on? When we look at one problem and the other problem, do a bit of pattern recognition, ask yourself what differs, what stays the same. You see that there's an x in both of them. It's staying on the same region. But clearly the only difference is the power. So there's something going on with this power that's making this either converge or diverge. Then the scientists would say, well, let's analyze it a little bit more. I really want to know what's happening here. So you take the interval, you would look at from a to maybe positive infinity, and you probably just want to stay away from 0 for the moment, because at 0, what happens to the function 1 over x, or 1 over x squared, or 1 over x cubed? It breaks continuity. I don't want to deal with that quite yet. So if we have this one, could we integrate it? Although it doesn't have a 2 or a 3, it just has something called p. Absolutely. Now, there is something I do have to be mindful of. What would happen if p was 1? Would this formula work now? No, because I'm dividing by 0. So back up here, I'll go back to my hypothesis, this whole entire scientific process, and I would say, okay, for this experiment, just make sure that p, I guess I have a row there, make sure it's not 1. Otherwise, we're going to have some problems. Start the clock again. Take this, drop it back in up top. We'll have b, 1 minus p, 1 minus p, minus a, 1 minus p, 1 minus p. And here's the question. What's changing in this problem? The b's changing. So if a's not changing and p's not changing, that's called a constant. What happens when you take the limit of a constant? Well, it's constant. It stays the same. Otherwise, it wouldn't be called a constant. So the limit really just applies to this part. Maybe take this negative, absorb it in, and let's just reshuffle terms a little bit. Because once again, hey, let's be more positive about life. Not to be so negative all the time. Take it, readjust it. And since, once again, p is not changing, b is, factor out the constant. So what's going to make it or break it is this part right here. What would happen p if you tip it over, and let's say you're over on this side, where p is going to be a half, a quarter. What's going to happen to this value? That's going to be positive, isn't it? 1 minus a half is a half. 1 minus a quarter is 3/4. So if I'm over on this side, where p is less than 1, then 1 minus p is greater than 0. If you tip it on the other side, suppose p is 2. What happens? It becomes negative. Why do I care? What happens when you have negative exponents? Now, if p was equal to 2 again, what are you going to do with that negative exponent? Take it and drop it. Recalibrate. And if your denominator is growing without bounds, remember b is going off to positive infinity, what happens? It gets smaller and smaller and smaller still. If my exponent stays positive, suppose p is equal to a half. Well, what happens as b grows without bounds? It's b to the 1/2. So we are looking at the square root. But again, the square root graph looks a bit like that. It's also growing without bounds. As the input values increase, so do the output values. So here it is. As long as I stay on this side, we're going to have convergence. If on this side, game over. We're going to have divergence. And notice else what we have here. If the b goes off positive infinity, it gets annihilated. It goes to 0. And just by daring to dream, daring to look at it a little bit more, we made ourselves a formula. If p exceeds the value of 1, we know exactly what's going to happen. This is going to correspond to a minus p minus 1. But if p is less than 1, or even if it equals 1, this is going to diverge. Game over. Well, these kind of integrals, these are known as your p integrals. And these are your p integrals over an infinite region. And I can use the p integrals as a way to help us to better understand what's happening with other integrals. All right. Now, before I move on, questions. How would I work this problem? Again, when I'm working with an improper integral, we have this issue of convergence and potentially also divergence. In order to figure it out, apply the definition. It's a limit definition. Take it and recalibrate it, stop the clock, yank out the integral, then integrate. How are you going to integrate this one? Will a good old U sub work? And if a good old U sub doesn't work, because that's a product. If it's an addition, real fast. So since I identify an issue of a product in the integrand, what technique might I want to follow? My parts. What would be a good choice for you? Probably X. Then du is dx. You don't have the complexity issue. So if this is u, everything else is dv. And how do I get a v again? Integrate your dv. What is the integral of e to the minus x? And once again, I am looking at the fundamental theorem of calculus, so I want to tack on the endpoints. On the b, I can assess it right here, or I can wait to the very end. It's really just a matter of opinion how you want to proceed from here. But I do see something. I do see this exponential, and it might be to my advantage to take it and factor it out. Okay. Plug in. So you plug in the b, plug in the 1, and that's a lot of negativity, isn't it? Let's turn it around, make it positive. That's better. Looks better. More presentable. After you do the evaluation, take it, plug it in. And if you know one more time, that's a Cal 1 problem, looking at limits. The Cal 2, that problem comes back to getting to the function. All right, so what's going to happen You pull that ripcord, you take B and you send it off towards positive infinity as fast as you possibly can. What happens here? The numerator goes towards positive infinity as well as your denominator. Oh no. What do I do in these kind of situations? Calling your friend, good old L'Hopital. Take the derivative up top. Take the derivative down below. Now, if you take B, bump it back up, throw it towards positive infinity, what happens here? It's getting closer and closer to 0 now. So what we have is 2 over E. Well, let's take it and let's flip it around. Let's say we're looking now from negative infinity up to 1, x e to the minus x dx. And again, I want to do the same thing. I want to assess to see if this integral converges or diverges. Well, once again, I look at the integral, I pull off the part that's going towards negative infinity. I take the integral, I rewrite it so I can apply the fundamental theorem of calculus. I stop the clock, I look at the integral, like we did earlier. We found out this is going to be negative e to the minus x, x plus 1. No need to reinvent it. We already got the answer right here, so use it. Apply the fundamental theorem of calculus, plug in the 1. So you're going to have 2, maybe negative 2, and then you're going to have e, maybe drop it down below. Drop in the a. When you drop in the a, you're going to have a plus 1, and then you're going to have this, like that. And again, you can take this and you could move things around. You can recalibrate it to make it a little bit more presentable. Less negatives. Assess the limit. Now, first off, a is going towards negative infinity. Is there an a here? No, so that's called constant. Nothing's changing. I really got to focus my attention on this part here. But I got a problem. I got a big problem. What's happening with a? It's growing without bounds in the negative direction. Isn't that a little confusing to look at, maybe going towards negative infinity? So what we can do is a nice little trick. Turn it around. Make it go towards positive infinity. But if I take it and turn it around, make it go towards positive infinity, I got to take all my a's and make them negative. I have to compensate. Okay? So be mindful of this. If something's going towards negative infinity and you can't see what's happening, try this. Maybe we'll see it this way. Just make sure all the a's again change polarity. Well, what happens when I have a negative exponent? Properties of exponents dictates you can take it, raise that thing up, and again, this is constant. What happens as a goes off towards positive infinity? Well, this part right there is getting kind of smaller, negative. But what's happening here? This thing is exploding. It's going towards positive infinity extremely fast. Exponential graph. It's just making it more and more negative. That's okay. But what we don't have is we don't have convergence. What we have here instead is we have divergence. Now, first off, is this a p integral? A p-integral looks a bit like this. Is that what I have? No, it's close though, but close is still not close enough. If it's not 100% spot on, it's not 100% spot on. So you can't use the formula. But I do have some kind of idea, maybe some intuition based upon what's happening with this, and that might be useful. In order to figure what's happening here, I can apply the limit definition. Stop the clock, integrate. I know I've seen this before. What was that again? Now I'm just kind of curious. What is the arctangent of 1? If I look at tangent, theta, and if I take the inverse trigonometric function, so the arctangent of tangent, since they're inverse functions, you get the argument back out of it. What's that tell you about inverse trigonometric functions? What's the secret? What are they? They're angles. That's all they are. So what I got to do is I got to think about, oh, no need a theta there. It should have been y. What I got to do is I got to think about, if I'm trying to assess the arctangent of 1, I'm really asking for what value of theta gets me 1. That's a 45. 45 degrees. Since we were working in terms of radians, that's not root 2 over 2. It's going to be pi over 4. Here comes the big question. B is changing. That's not. It's constant. So look at the limit. What's happening here? Oh. Well, let me ask you this question. You guys remember the graph for arctangent? No. Should I remember the graph for arctangent? Yes. What is the graph of arctangent? It's like this. It's like you're swimming. If you look at the graph of tangent, that's the graph of tangent. So if you take it and topple it over, it looks like that. You're going to have a horizontal asymptote. 2. So amongst all the inverse trigonometric graphs you need to know, this is the top one right here. The inverse sine, inverse cosine, inverse secant, yeah, they're interesting, but truthfully, guys, they're not going to help you out in a lot of different calculations. Every so often they do pop up. Arctangent pops up all the time, and we're seeing that with our partial fractions decomposition. So it might be to our advantage to really see what's happening with this arctangent graph. Riddle me this. If B keeps marching on and on and on and on and on and on as it races off towards positive infinity, what's happening to the graph? It marches on and 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 on, but where's it going? We have convergence. Well, that's interesting. Well, let's take this and let's flip it around. Let's say we're going to negative infinity to 1. And again, I'm looking at an improper integral. And when I'm looking at an improper integral, I can't apply those proper characteristics of the fundamental term of calculus. It's a different beast. Guys, it's a different type of integral. So I have to apply the definition. Write in terms of a limit. Stop the clock. Figure out the antiderivative. Again, we see the arctangent. We'll have the arctangent of 1 minus the arctangent of A. Tangent of 1 is 4. Big question now. What happens as A races towards negative infinity? So it's going this way, and then here, then here, then here, then here, then here. If you're on the graph, like a slide. You're sliding down where? Pi over 2. We have convergence. Now, when I go back, I see that this integral converged, this integral diverged. But when I flip it around for this one, they both converged. And if they both converge, this will also converge. So here's how you would work these kind of problems. If you're given this problem, goes from negative infinity to positive infinity, you can take this and you can break this up however you want. It's your choice. You can break this up and you say, hey, I want to see what happens from 2 to infinity. Go for it. You say, well, I don't want to do this. I want to see what's going to happen from 12 to positive infinity. Do it. It's your choice. Break it up however you like. But then you're going to need to assess it. But if you look a little bit ahead, you might be able to use some kind of strategy. Not only can you go from 1 to infinity, it might have been better to start it off at 0. Because if I started off at 0, what's the arctangent at 0? 0. And it's going to zero it out a whole lot faster and get you the answer a whole lot faster. But it doesn't really matter. This is going to correspond to the sum of this integral and for the integral down below. If it does not converge, then you cannot do this. This is not the definition and this converges. I cannot say that the double-sided integral that diverges. So here it is. If I want to see what happens for this, what I need to do is just look at one side, just one side, guys. And if one side diverges, that's it. This will diverge. There's no need to keep looking for something after you found it. If you found an integral, this part diverged, don't do this. You're wasting your time. It diverges, go about your business. There is one more issue here. Mistake. When people are going about this kind of problem, they're going to take this and they're going to say arctangent, then they're going to do this. Then they're going to do this. In that. What are you applying here? You are applying the fundamental theorem of calculus. But the fundamental theorem of calculus is only applicable when you have those proper characteristics. Continuity on a finite region. I don't have that anymore. So I can't apply the fundamental theorem of calculus anymore. So you have to be really careful. So what? Who cares? Suppose if you're building a bridge and you base your assumptions on faulty reasoning. Eventually, it may not happen all at once, but eventually it's going to all come crashing down, leaving you in the dust. So just be careful of this. I do watch out for this on exams to see if you guys do this or not. You might get the right answer, but just because you get the right answer doesn't mean you did it the right way. Favorite example, take 64 over 16. Equals 4 because we cross out the 6's. Or 95 over 19 because you cross out the 9's. But that's not how math works. This is not how this works. All right, guys, that's all the time we got here for today. I will see you tomorrow. Have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.